Folks, we are headed toward Industry 5.0. Doesn't it seem like we just started talking about Industry 4.0? So, what should we expect from this next industrial revolution? Well, we know for a fact that our industrial designs will need to get smaller, faster, and smarter, and energy efficiency will reign supreme. So, if energy efficiency is paramount, then we're going to need to talk about power conversion, EMC, EMI, power factor correction, and a whole lot more. Hi, I'm Amelia Dalton, host of Chalk Talk. Energy efficiency will be a critical concern for Industry 5.0. In this episode of Chalk Talk, Alessandro Maggioni from onsemi, Simon Reuning from the YAGEO group, and I explore the implementation of the various stages of power conversion. What steps we can take to make power factor correction more effective, and how you can take advantage of onsemi and YAGEO group solutions for your next industrial design. And before we get started, don't forget to click that link. There you can find even more information about this topic. Hi, Alessandro. Thank you so much for joining me.
Thank you, Amelia. It was a pleasure.
And hi, Simon. Thank you for joining me.
Hey, Amelia. Happy to be here.
Excellent. Okay, so Simon, let's talk about the industrial revolutions. Tell us how we've got to where we are today and how industrial revolutions have shaped today's factories.
Yeah, that's actually a really good topic. When we start looking back at the evolution of the Industrial Revolution, we really start at the early ages, starting in the 1784. That's when the Industry 1.0 has really started. That's when we had the mechanized production, steam power in the textile industry, when it really started taking off. Then we move down the timeline and we go into the Industry 2.0. That actually started like in 1870, and that's when we started having the mass production. That's when electric power was eventually introduced. And that's also when we started having a little bit more of the assembly line type of work. Then 100 years later, we are looking at the Industry 3.0. That's when we have here 1969, so that's fairly recent. That's the automation systems. That's when computers started getting integrated into the manufacturing process. That's also when really the electronics revolution started. And then only 50 years later, we're looking here at 2011. That's when we are at the Industry 4.0. And that's kind of the area where we're in right now. So we're talking about smart manufacturing. That's when IoT connectivity is really introduced. And that's also when we have a lot of types of data analysis happening. So one important thing that we are looking at here from the timeline, the first 1.0 to 2.0, 2.0 to 3.0, that was 100 years each. Now going from 3.0 to 4.0, that was only a 50-year time span. So it seems that the Industrial Revolution is really accelerating. So that's really something that we have to focus on, because 2011 is already long past. So that means, when is the next step going to be, and what does that mean for us? So now that leads us to the point of the Industry 5.0. We don't really know exactly when it's going to start, but we do know that that means for us that it's going to be smaller, that's going to be faster, that's going to be smarter, and that's going to be more efficient types of products that we're going to have to implement. One of the things that I like to think about is my grandfather. He grew up in 1928. Back in those days, he still had to drive to the city with a horse-drawn chariot. Now, when he passed away, he was actually able to use an iPhone. So that was a huge and drastic difference from the technology area. And I think with Industry 5.0, that's going to be as drastic of a change for us as we're looking forward into what that's going to look like for us.
Fantastic. Now, with all of these advancements, the demand for energy efficiency is certainly growing. So, Alessandro, why is energy efficiency now a critical concern for industries?
Let's take an example which everyone knows of. Let's relate this to Amazon, for example. No? So you can buy pretty much anything, and you can have it delivered to your front door basically the next day. All of this is enabled by AI and real-time data. So factory automation really impact everyone here every day. With growing adoption of the Industry 4.0, so this means that, for example, automated system, real-time data, real-time monitoring, and also smart technologies integration like IoT, AI, and digital twins. If you take all those systems are integrated together to make the manufacturing process really more efficient. Will helps to have a better forecastings and also helps to reduce the downtime in a continued process optimization. Each automation steps also brings with it several applications that we have to consider when looking into energy trends. So for example, more automation means, for example, more motor drivers. That also means that more power supplies are needed for additional equipment. So taking all this into account, we have there's a serious case for energy efficiency that have to be solved. If we say here, so energy efficiency is becoming increasingly critical as we face, for example, grid limitation. So due to rising energy demands and aging infrastructure, it's a problem, and increasing loads. The power supplies we use must be careful considering to handle the higher capacity requirements. All of those are driven by additional equipment and also to peak demand. So this is in particular evident in area with the increasing daytime manufacturing activities or even operation are not 24/7. On top, you need to take into consideration that energy efficiency is not just about the cost saving with the factory. It's about maintaining a competitive edge. If factories fail to optimize the energy use, so the rising energy cost could outweigh the benefit of automation, and also it's eroding the long-term profitability. To illustrate this, we can consider an hypothetical graph showing the increased energy consumption associated with the great adoption, for example, of industrial automation. So the projections highlight here the urgent need for engineers to prioritize the energy efficiency in a factory process. So ensuring that the sustainability and the cost effectiveness of an automation continues to grow accordingly.
So, to improve energy efficiency, we need to focus on power conversion. So, Simon, can you walk us through the stages of power conversion?
Yeah, absolutely. So, looking at the stages of power conversion, and that's really the foundation of energy efficiency. And I think it's really important for us to understand each one of those aspects so that we can design the best types of products going forward. The first step would be the EMI filter. For the EMI filter, we have some main requirements that are needed from the EMI filter. That would be noise suppression, that would be an efficiency boost, and that would also improve reliability by reducing noise stresses on the overall system. So as you start having an EMI filter in your overall system, that means the noise is not passing through, not causing issues down the line, which could cause you any type of reliability issue. In addition, that noise could cause inefficiencies down the system. So that's really important to have an EMI filter in that system. The next stage would be your PFC. Now, with the PFC here, we're optimizing the power use. It really allows us to be more compliant with any type of requirements that we have law-wise. And it also helps us with energy savings because without a PFC, the product would be much more expensive to the energy suppliers for that type of product. Now, down the line, we have the DC to DC converter. Here, we're looking at high efficiency, compact designs, and also thermal management. Right? As more and more efficiency is required, we really need to have good DC to DC converters and technologies that go into that to really allow us to have high efficient power supplies at the output. And then the last stage would be the output filter. So now with the output filter, we have a little bit of ripple reduction. There's also going to be enhanced performance on the product. And it also minimizes any type of losses that we would be experiencing.
Simon, talk to me about the reasons behind EMI filters.
Absolutely, yeah. When we look at EMI filters, I think this is actually a very common question that comes up quite often. Why does an EMI filter even exist? Well, the first thing is we understand the requirements already. We've discussed this on the previous slide. But when we start looking at EMI, it is actually part of a bigger picture, and that is going to be called the Electromagnetic Compatibility, EMC. So EMC all across the world has laws and regulations that determine exactly how much electromagnetic noise a product can have. And there's all kinds of regional standards, there's international standards, and all of that is then broken down into two types of categories. The first category is where our EMI filter lives. That would be the EMI, which is the electromagnetic interference. Now, with the EMI filter, the goal is to filter out any type of radiated emissions or any type of conducted emissions. The other part that we're not going to cover here today is going to be the EMS, which is the electromagnetic susceptibility. That is any type of radiated immunity and conducted immunity. Now, when you look at the EMI filter and you want to understand exactly what does this product do and why do we need it, it is really noise containment. It makes sure that no noise is coming out of your system back onto the lines, no noise is being radiated or noise within the limits regulated by law. And then the EMS system would be how easily is your product influenced by outside sources. If you have a toaster next to your microwave, is the microwave going to influence the toaster when it's turned on? You don't want to have that. So that's why this would be an important factor. But for today, we really just want to focus on the EMI because that's one of the important factors here.
That makes sense. Now, speaking of EMI filtering, how exactly does an EMI filter work?
With the EMI filter, a lot of times it can be a little bit overwhelming when you start looking at it. But breaking this down, this is actually very simple. When you look at an EMI filter, there's really just two types of noises that you're trying to filter. The first one would be the differential mode noise. As the name indicates, that is noise that is different on both lines. So you have an AC input, there's 3 lines going in, one is going to be the ground, the other 2 is the ones we're talking about right now. So if you have noise on those lines that is different from one another, we need to be able to filter that. That's where we use the X capacitors. And X capacitors are connected line to line. Now, the next type of noise would be the common mode noise. Again, as the name indicates, it is common on both lines, but is measured in reference to ground. So in order for us to filter that, we use Y capacitors, and those Y capacitors are then connected from line to ground. Now, to tie everything together, we need to have a common mode choke, which really makes your final filter. So in order for you to have an EMI filter, you will need X capacitors, Y capacitors, and a common mode choke inductor, and that allows you to block any type of high frequency noise. Now, once you have all of these components in place, that allows you to reduce any type of radiated noise or conducted emissions that you're dealing with. And that usually helps you meet the standards. You might have to do some adjustments based on capacitance values or common mode choke values. Once you have that system in place, you have your EMI filter. One thing that's also really important on the EMI filter is what happens when it fails. Because if a failure occurs, they need to prevent any type of shock or fire. So that's why oftentimes when you see X or Y capacitors, they're actually referred to as safety capacitors.
Okay, so once EMI is managed, we need to move on to power factor correction, right? So, Alessandro, why is PFC necessary?
Well, the purpose of a power factor corrector, or so-called PFC, is basically to improve the efficiency and the stability of the electrical power system, basically by, in simple words, aligning the voltage and the current waveform in an AC power system. So this is ensuring the optimal power delivery to any load. So if we break a little bit into a little bit more explanation, we have, so why does a PFC exist? First of all, we have the reactive load and the power factor. The reactive loads, for example, motors, transformer, or any inductive circuits, cause the current and the voltage waveforms to become out of phase. So the power factor, or PF, is basically the ratio of the real power, which is the one which is really used to perform the work, and the apparent power, so which is the total power supplied. So a low power factor means a very poor power utilization. This means that when you have a low power factor, so the results are that you have increased energy losses, you have overburdening of electrical infrastructure due to the fact that you have a higher apparent power demand, and last but not least, you also have a higher electricity cost due to the fact that the penalties you have from your utility companies. The second point is that you have load requirements. So many modern devices use switching power supplies for efficiency, which are by definition not linear loads. So those loads draw current in sharp pulses, rather than very smooth sinusoidal waveforms, and are distorting the current waveform. So this distortion introduces harmonics, which further reduce the power factor and cause an additional losses and interferences in the power system.
Okay, so Alessandro, can you explain how PFC is implemented?
Sure. How does a PFC work? So basically, the PFC aligns the current waveforms with the voltage waveform to improve the power factor and reduce the harmonic distortion. So let's see in details the working principle. So, okay, you have a current and voltage curves. So without PFC, the current waveform lags behind the voltage waveforms in any inductive loads, or leads. So this is a true incapacitive load. Additionally, nonlinear loads can cause spikes or dips. So this is also distorting the current waveforms. With the PFC, the current waveform is reshaped in order to match the voltage waveform in both phase and shape, and helps to ensuring a complete sinusoidal behavior. There are different types of PFC. You have the passive PFC. This is using passive components like inductor and capacitors, so in order to filter and smooth out the current waveform. Are simple. are cost effective, but they have a limited in performance and size. You also have active PFC, so which are using active electronic circuitry, including transistor and diodes. So those are controlled by feedback mechanism to precisely shape and the current waveform. Are more efficient, are suitable for high power application, and they helps to comply with stringent regulation. So which are the process of the active PFC? You have the input stage, so where the rectifiers convert the AC to DC. However, the DC signal includes ripples and harmonic. You have the control loops, with a feedback control loop monitor the voltage and the current waveforms, and a PFC controller dynamically adjusts the input current to maintain phase and waveforms alignment with the AC voltage. And then you have the output stage. So to smooth the DC voltage is fed to the low, whatever it is, to ensuring an efficient operation. Then if you can summarize, the benefit of a PFC are that they are improving the energy efficiency. This helping minimize the waste reactive power. It reduced the heat generation in wires and components, so this also extending their lifespan. It also helps in the requirements to meet a regulatory standard, like for example the ISC 61000-3.2 for harmonic distortion, and also helps to lower the electricity bills and avoiding any power factor penalties. So how to move then from left to right? So which is the solution? Basically, you need to shape the input current in order to match the input voltage and the waveform. Okay, so this is the goal. So how? Insert a switch mode boost converter stage between rectifier and the bulk storage cap.
Okay, so Alessandro, how could we make PFC more efficient?
Always remember the golden rule. So better efficiency with fewer devices in the conduction path. So this is the golden rule for be more efficient. So for example, here on the right side, you have the typical PFC with bridges, diode, MOSFET, and so on. On the left side, you can see a bridges totem pole configuration. The bridges totem pole configuration consists of a two half bridges configuration. One half bridge, which is commonly referred as a fast leg. This one switches at the PWM frequency of the controller. And the other, which is commonly referred to as low leg, switch at the AC line frequency, so 50 or 60 Hz. The fast leg switches perform the role of the switch and the diode. If we consider a classical boost PFC, the switch's function is to regulate the output voltage and also shape the input current to provide the high power factor and a very low harmonic distortion. On the other way around, the slow leg switches perform the role of the diode bridge, so in a classical boost PFC. So an active switch with a very low on resistance are utilized instead of diodes, and this results in improving the efficiency. So the totem pole PFC operate with only one slow leg and one fast leg device in the conduction path, where the conventional boost PFC operated with always two bridges diode, one active switch, or the boost diode in conduction path. So this means that fewer devices in the conduction path and active switches replacing the bridge diodes allow the totem pole PFC topology to achieve a higher system efficiency and higher power density than the classical boost PFC. On top, the totem pole PFC is a derivative of a standard boost PFC converter, so where the bridge diodes, as you mentioned, are removed, and therefore the booster circuitry directly interface with the AC input. So here, the key challenge with this approach and where is the patent and are needed are that the detection of the line polarity, the current sense, the current limit implementation is important point to take into account. On top, a totem pole PFC is a synchronous boost converter, as opposed to a standard boost PFC implementation with is asynchronous. So therefore, a zero current detection scheme is always needed to be implemented, as always seen an unrectified AC voltage line. It's also important to note that similarity to a standard boost PFC, if you are a designer, the criteria for selecting the boost inductor, the output capacitor, the boost FET are very similar between a totem pole PFC and a standard boost PFC.
Alessandro, the next step is DC to DC conversion. So why do we need DC to DC converters?
Basically, a DC converter are essential in all the modern electronics and power system because they allow an efficient voltage regulation and power conversion in device which require a different voltage level. The primary function include, for example, a voltage level adjustment. So many electronic devices operate as very specific voltage level, 3.3 volt, 5 volt, 12 volt, and many more. A DC-DC converter step up or boost, a step down or call back the input voltage to meet all the requirements of the different loads. It's also important for power efficiency. So by regulating the voltage and the current, a DC-DC converter improves energy efficiency in devices, minimizing heat generation and energy waste, especially when we are talking about a higher ratio and higher load. Load changes. A DC-DC converter ensures a stable output voltage when load changes. Compatibility with multiple power sources. A device is often used in multiple power sources, for example, batteries, solar panel, USB power, standard lines. So a DC-DC converter always ensures the compatibility between these sources and the device's power requirement and the application in industry. So they are using everywhere. So they're using in industry, they're using telecom, in telecommunication, in automotive, also in electric vehicles, so industrial automation, all the kind of renewable energy system that helps to manage the power efficiency efficiently and reliable.
Okay, so Alessandro, how do DC to DC converters actually work?
So basically, we can see here some different basic schematics. So the buck, the boost, the LLC, the flyback, and so on. So how it works? A DC converter works by transferring energy from the input side to the output side while adjusting the voltage and the current accordingly to the desired output. So this is the main job of a DC-DC. So this process involves energy storage element like inductor, capacitor, and switches. Key types of DC converter includes buck boost, LLC, and flyback converter. So those are the most typical type. Which are the basic components? We have inductor and capacitors. So those are storing or releasing energy to smooth voltage and current. We have switches, MOSFET, IGBT, GaN, SiC. Those helps to control the flow of current by rapid switching. We have diodes, so which are direct current flow and prevents reverse current. We have the controller, which is the one, the brain which maintains the desired output voltage by adjusting the duty cycle of the switch. And we have the transformer for an isolated converter, which provides electrical isolation between the input and the output. So we have different operating principles. So we have the buck converter, or so-called step down, which is stepping down the input voltage to a lower output voltage. Those are using a switching element like MOSFET or others to chop the input voltage and an inductor to smooth the resulting waveform. You have the boost converter, which is stepping up the input voltage to the higher output voltage. So it stores energy in an inductor during the switch on period, and it releases a load during a specific off period. You have the combination of two, so the buck boost converter can step up or step down an input voltage depending on the configuration. Typical example is a battery when you have the input voltage which is changing widely while you have a fixed output voltage which is across the level. It operates by inverting the polarity of the output voltage. Another topology is the LLC resonant or resonant converter. It is a very high efficiency isolated converter that uses a resonant circuitry, which is based by the inductor and capacitors in series and parallel configuration. It operates in a soft switching mode, so this means zero voltage switching or zero current switching, and it reducing the switching losses and improve the efficiency. The transformer isolates the input and the output, and the resonant tank regulates the energy transfer by tuning the operating frequency. It's very common in applications which require a very low noise, high efficiency, and a compact design, for example, server power supplies. You also have the flyback converter, which is an isolated converter, which is commonly used in relatively low power application, say up to 30, 50 watt, more or less. It's used a transformer to store energy during the switch on period, and it transfers it to the output during the switch off period. It's a very simple design. There are few components which can able to make it very cost effective, and are used mainly in chargers, adapter, or in some auxiliary power supplies in the industrial control system. So also here the key stages are the input stage, where the voltage is supplied from the power source. You have the switching stage, with you have a high switching frequency, which alternates between on and off state, regulating the energy flow. You have the energy storage stage, where the energy is temporarily stored in the inductor, capacitor, or the transformer to ensure a smooth voltage delivery. And then you have the output voltage stage. The voltage here is filtered and regulated to match the load requirement. This helps to ensure a stability and a precision, high precision of the output voltage. So the advantages are compact and lightweight, especially compared to some linear regulators. High efficiency, often exceeding 90%, especially in some LCS converter or some step-up converter. Versatility, so it can handle a wide range of applications, really from very low power adapter to high power industrial system. It has isolation, especially for flyback and LC, which ensure the safety, reduce noise, and also prevents ground loop. And low noise, especially for LLC, which are particularly suited for application requiring a low EMI and noise performances.
All right, so the last stage we need is output filtering. Simon, why is an output filter necessary?
Well, looking at all the different stages that we just had, we've done a lot of work to trying to filter out any type of noise from the EMI filter through the PFC. We try to optimize the output voltage for the DC to DC stage, and we're trying to be as efficient as possible. Now, when we come to the output stage, not having a filter would mean that we would have a very noisy signal. Alejandro mentioned that there was multiple microcontrollers in a system. Those microcontrollers are going to have different types of voltages. Now, when you look at the input voltage requirements of those devices, a lot of them aren't able to handle large voltage fluctuations. They need, when they say 3.3 volts, they probably need 3.3 volts within 0.1 or 1% tolerance. Now, if you don't have an output filter, that means your output signal could vary quite a bit. Here in this example, just to show you guys what it would look like without a filter, we have a 5-volt output. Now we have a ripple on this. This would be 1 volt peak to peak. So we have plus 5.5 volts or plus 4.5 volts. So there's a 1 volt difference in what the output voltage will actually look like. So we have done all this hard work to get to the output, to have as clean and efficient signal as possible. But now we're looking at the output filter. We're not filtering anything. So that means our whole work was essentially for nothing. So that's why it's really important to have the output filter. Now, once you implement an output filter here, you can see that there's still some noise on that signal, but it's so minimized that essentially this output signal will look like a 5-volt DC signal. And that's really important for all the devices that are actually connected to this output voltage, because that means that they can operate correctly. If you have something that is very sensitive, like imaging or something in that type of application realm, they need to have an accurate input voltage in that case that allows them to generate accurate images. I mean, you wouldn't want to go take an X-ray and then your image comes back all fuzzy and you can't even tell what's going on inside the body. So you want to make sure that there's an accurate output voltage that gives you a very nice DC signal so that whatever you do with that voltage is going to give you wonderful results.
That makes sense. Now, can you walk us through how output filtering works?
Absolutely. So looking at the output filter, there's going to be a couple of components involved. So the first one, I think is very obvious, is going to be a capacitor. So the capacitor is really there to reduce any type of voltage ripple, and it absorbs noise from voltage relations. The next step would be the inductor. So the inductor here is there to reduce any type of current ripple. So it smoothens out any type of power delivery. To put these two together, you essentially get your LC filter. Now, the LC filter is really important because it has extremely low loss. That means that we have done all the efficiency boosts possible in the previous sections. Now, here at the output stage, we also want to make sure that we have high performance and really minimize our losses. And that's where the LC filter is perfect for. That allows us to block any type of high frequency noise. And it also smoothens out the voltage and the current ripple that the capacitor and the inductor filter out. One other one that I want to mention more as an honorable mention is the RC filter. Now here we're mostly talking about power, but sometimes you need to have feedback and signals. And for that area, you might want to do a little bit of signal conditioning. And that's where an RC filter could be useful. But over the resistor, you will drop a lot of voltage, and that is done with power loss. And so that's not an optimal filter for any type of output power stage. But if you need to have any type of signal conditioning, you can use an RC filter, which then dampens any type of oscillation and really helps you signal conditioning your signal that goes through that type of filter.
Now that we understand power conversion, where do onsemi and the YAGEO group fit into this ecosystem, Simon?
Well, in the beginning, we talked about the Industrial Revolution. One thing that we want to look back at is that Back in those days, a steam engine would produce something around 3.5 kilowatt. It will also take up the entire room. You can see here on this picture that steam engine is really built in the entire room. You can see on the right side, there's a man for reference, just to see how large this type of device would be. But now, as we have moved into the current time period, you can look at a Tesla V3 supercharger that is only 7 feet by 3 feet by 2 feet wide. So it's not a very large device, and it can produce 250 kilowatts. So that is so much more power. So that means to us, this is a very different types of area. We're not doing the way we used to do things anymore. And I think for going into the industry 5.0 and just really having in mind energy efficiency, we have to think a little bit different, because that mechanical area is very different from our silicon area that we're in right now. So what is the next step and how does that look? So that means our technologies really are facing new challenges. And the new designs that are coming out, they need to have these technologies that we're developing. So really, it's like an ecosystem where the design engineers are working on the new products to make it more efficient. And we are developing products for those designers, passive components and active components, so that help them with the challenges that they're facing to really optimize the overall systems. And that's where we come together with the passive and with the active components to allow the designers to develop those products that really get us to the next stage. And that's really what we are focusing on. And that's where we are trying to help the design engineers with their challenges, get the products out there, get them more efficient, and develop products that helps them face those challenges easily.
Fantastic. Now, can you guys talk about an application example here?
Yes. So if we can see, for example, here we can see a showcase of a single-phase power conversion system, in this case using silicon carbide technology for the primary side and MOSFET for the secondary side. So this is a system which is designed for power deliveries between 1 kilowatt and 3 kilowatts. So this system is divided into several key components, as we can see here. So from the left side, you see the totem pole PSC, so the number one, which utilizes a bridge and totem pole PSC topology for efficient power factor correction and eliminate the input diode bridges and improve the efficiency, as we discussed previously. We have a non-isolated driver for the slow leg of the totem pole, which is controlled the slow leg of the totem pole PSC, also ensuring an efficient operation with a standard superjunction FET. We have an isolated gate driver. Those are used to drive the fast leg of the totem pole and the half bridge of the LLC, ensuring a precise and efficient controls. So those are based on silicon carbide technology. LLC controller, so on the secondary side, it manages the LLC operation, driving for the next stage. And then finally, we have the output rectification and the filtering, so which is produce a stable and high performance DC output. Here, the physical layout at the bottom also illustrates the actual implementation of on a PCB, highlighting the high integration of the advanced SiC technology in this case. And also this technology offers a higher efficiency, they reduce the size and improve the thermal performance compared to the traditional silicon-based system.
Yeah, and then in combination, this is really where it's reflected here as how our ecosystem is. Sometimes it can be a little bit overwhelming with all these different technologies that these companies provide. But here with onsemi and YAGEO Group, we try to make it easy for the user to understand exactly of how our products fit into your power supply. So here we have this laid out into these 4 sections that we talked about today. We have the EMI filter, we have the PFC, we have the DC to DC converter, and then we have the output filter. And we're showing you exactly which types of components we offer that can help you in those particular areas. For the EMI filter, you can see here, we have the safety capacitors and the common mode choke. We also have for the PFC, the totem pole PFC drive. We also have the PFC inductors. And all of those components are just very simply put onto one page. So that makes it easy for you to utilize this, understand exactly of what we offer and how we can help you in each of those sections. And as you can see with onsemi and with YAGEO Group together, you can essentially design this entire single-phase power supply without having to use anybody else, because with our 2 components combined, we can make and help you design this entire product. And that's really where we come together and have a wonderful ecosystems with the passive and the active components. And this here is a really good representation of that.
All right. Can you guys summarize your key points for me?
Sure. So basically, we have 3 major key points. So system level thinking. This helps to have a optimal performance. Means that you have to think from the beginning to co-design active and passive components already from the start to have the better performance of the system. You have to think about efficiency and reliability. Proper power conversion helps to minimize losses, increasing efficiency, improving the thermal performance, and also helps to have a long lifespan of the overall system, because we need to take consideration that those systems are quite very expensive. So this is something you have to be taken into consideration. Also, the fact that onsemi and YAGEO group have a completely complementary ecosystem. So this helps from the beginning to delivery a full advanced semiconductor and high-performance passive system for all industrial automation system.
If there's just one thing that I would ask of everybody is to really go ahead and explore our solutions. We have everything here on our landing page where you can look at the different types of products that are going to be available and see how those types of components can enhance your efficiency, reliability, and any type of compliance that you might be struggling with. It is also really important to look at those technologies that we're bringing out, because oftentimes designs are copy-paste. This is what I've done last time. I'm just taking part of that design and redoing it. But go ahead and explore some new solution, because we find better ways to make our products as well. So we are improving our products, which can allow you to have a smaller component with more power, or a smaller component with similar power levels, but is significantly more compact. There can also be cost savings involved with that. So it is really important, and I would really encourage everybody to explore the solutions that we're offering. Also, if you have any questions, always feel free to talk to our experts. We both have wonderful design teams, and we have FAE teams that are always willing to help to work on your designs and get you any type of tailored recommendations, especially as it can be kind of overwhelming looking at the portfolios of both companies. But just give them a call, give the experts a call, and have them help you in your overall designs. And then the other part is also important to stay ahead. So keep up with the evolving technologies and with the evolving power design trends that are actually coming out. And as you start seeing of which direction those design trends are going, that also allows you to design better power supplies in your overall system. That's really something that can optimize factory automation. And so with that, I just want to really encourage everybody that we can build a future together of intelligent factory automation.
Well, I think that's all I have time for today. Thank you so much for joining me, Simon.
Hey, you're welcome. It was a great time.
And thank you for joining me, Alessandro.
Thanks, Amelia. Thanks for the time here.
And before we go, you didn't forget to click that link, did you? There you can find even more information about this topic. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talk section of EE Journal. You can't miss it, it's right across the top. Or head on over to YouTube, youtube.com/EE Journal.